loading and shear stress due to shear loading to find the complete state of stress. Once you know the shear force and the bending moment acting on it for the given loading and also the support condition, you can find the stress. We can find the superimpose these effects to find out your stress by multiplying, because the loading, if you want to stress from load, it is P over A, right? If you want moment, stress is equal to, sigma is equal to, anybody? Let's do the revision before I go into do the stresses. We done some of the stresses, but now we have to go deeper into finding the stresses using, before stresses, the bending, we must know in and out of how to find shear force, how to find bending moment, how to find the maximum, where it is zero, where it is maximum, what are the profiles, shape of the profile, right? When it is contra, right? What are the contra points of contra? All these things you should know to find the stress as the next step. Right? A small revision on engineering dynamics for finding shear force and bending moment. If in the building construction, it has beams and columns, right? Any building, any frame structure, any frames will have beams and columns. Beams will be running this direction, 1, 2, 3. Columns 1, 2, 3, 4. Like this, columns and beams are forming your structure, connected by connecting the slabs. Slabs, don't worry now. Let's do the beams and columns in this module. When you due to this loading, start from here. This is a foundation, it's a basement or foundation. This column is supported by this basement, and our entire loading is acting onto this structure, right? Due to this, it will bend like this, and then like this, like this. When if you take the space frame analysis and the result of space frame analysis, the frame structure, you will have these types of bending. Here, if you look into this one, is sagging, and then hogging, sagging, hogging, and then sagging, sagging, a bit of hogging, and then again sagging, hogging, sagging, hogging. Like that, you have a different types due to the number of loading. When it goes here, you take this one. When it goes here, it's only this much loading, not many, right? It's already the other end is conveniently supported by all these things, right? So you hardly have this much loading only. So a little bit sagging, not very high. As you go along, you will have different shapes of the bending moment profile and corresponding shear force diagrams. So we are doing this part only. You must know where we are, what we are doing. We are analyzing this structure which has beams and columns. Quickly recall the loads that you will be analyzing. In any beams and column, right? In any beam and column, you will be subjected to dead load, the self height of the member itself. Right? If you say so cross section as steel member 20 by 20, then you have the self height of the member itself equal to 20 by 20. The area 20 by 20 times the intensity. Right? The density of the material, if you calculate, you will get the weight. So you have dead load, live load, all the moving load, all the objects which is in dynamic position condition, inertia and the forces. In addition to that, it will create its own responses, right? Sometimes it will form as a loading to the other end or to the following members. So you need to calculate, this, what is the inertia of the member before you select. And then finally, centrifugal force, loads or forces, just the forces, other types of forces that are acting on it. It may be other type caused by other types, not apart from this dead load and live loads and this type. Right. If you talk about the mode of loading, it may be a point load which is concentrated at a point or distributed. It may be distributed or spread over the member to a certain distance. It may be from whole member, a part of the member, or at support from some distance from the support, and so on. So that is called distributed. You should know it. And these types of loading based on the response of the member, we call this as, it's a kind of a tensile load, compressive load, it's a twisting load. If the member is twisted due to the load, it is called twisting load. Bent, the member bent means bending load. Shear, only shearing caused by the load, it is called shearing load. So you must know these classification. Introduction, types of beams. You must be knowing types of beams, effects of loading on the beams, the force that causes shearing. Force that causes shearing is known as shearing force, right? 1 over the layers. The layers will show it's not a whole member response, but layer in between the layers they will respond, or there may be a crack at the particular layer only, and it's called shear. Because of the one layer shearing over another. The force that results in bending is known as bending moment. We can draw these diagrams. Loading, it may be shear force, effects may be shear force or bending moment. Altogether, we put the effect, the response of the member to withstand the load, or like this, all the vertical load are converted into shear force, horizontal load are converted into a couple, which is bending moment. By means of these two responses, the member is stable for any type of loading that is coming on the building or the member. Accordingly, how you design as an engineer, want to design for how do you give the response to the overcoming load? By designing a shear reinforcement, all the ribs, all the links that are connecting the reinforcement. Later you will study about this shear reinforcement. This is the covering one applied horizontally like rings. I will show later. This is not main concern of this study. But shearing reinforcement will be all the rods are provided horizontally and are bound by the rings at some spacing. Shear reinforcement. And the bending moment by design flexure reinforcement. Whether it's a tension or compression, you will provide the rod at the bottom. If it is the tension at the bottom, if it is both compression and tension, then you have to provide rod at the top and bottom to withstand the loading or keep it in position. All these things are determined by using equations of equilibrium or equilibrium equations, which is sigma f is equal to 0. All forces acting in y x direction equal to 0. All forces acting in y direction equal to 0. And the moments about any support or any point should vanishes. If there is any moment, then there is a failure. There is a bending. Bending should be 0. Keeping this condition, applying this condition, we can find the unknown. Let's see how we are finding out. Principles of moments. Are you following? Any questions so far? Right. The moment of a force indicates the tendency of a body to turn about an axis passing to a specific point O. Moment is always acting about a point or about a section. Mostly it is about a section because it has directions. Better to follow by about a section or an axis, right? And otherwise a point. Always about a point O. Point O. Okay. These are the examples you are seeing here. The principles of moments, which is sometimes referred to as Varignone's theorem, way back in, say, 17th century, about 17th, 18th century, they followed this one. Maybe Greeks and Roman, they are the one pioneer for our civil engineering construction. Rome, Greeks, Athens, buildings. The moment of force about a point is equal to the sum of the moments of the forces, components of the forces about the point. That means it should nullify. The moment should nullify. The resistive moment should be nullified so that the member is stable for any type of loading that is coming on. That's the meaning of this one. In two-dimensional analysis, if you treat this, all these types of behavior of the members, the operations, then it will be M equal to force into distance. Always the formula is force into perpendicular distance. That is the moment. For example, this one, if you consider, this is the axis, and this is the axis here. The force is applied here. 5 wrenches are used to rotate, right? Rotate means you are applying a couple to rotate, and maybe it is a removal or fixing, any type of operation going on here. It is being rotated, right? The force is acting at a distance from the axis. From the axis of a plate. This is the point where you need the job done, right? The focal point. And you apply the force here. When you apply the force, it will be different. When you apply the force, it will be different. Why? And going here, again, this is the pulley, this is the middle point you are applying, and the wheel, right? To rotate this, is applying the force here. Again, for this force, to find out the moment, you need to know how much force you are applying times the distance. Make the job done, right? The bolts are fitted or screw in or screw out. Both can be by applying the force in the respective direction, right? Same goes here. This may be an object, maybe a rotating object. Then this is the center. To find the moment, you need to know how much force to be applied to rotate and the distance with respect to the axis of rotation. These are all the moments are determined. So frames. When you go for analysis of frames by applying moment distribution method, the stiffness matrix method, you will follow this indeterminate beam. Now all determinate beam. Until stress analysis and design, you will analyze only determinate beams. What is determinate beams? Means this is following the equation. Have to follow all sigma f is equal to 0, all sigma fy is equal to 0, m is equal to 0. If it is complying with this, then your member is said to be determinate beam. That means the number of unknowns is equal to number of equations you have. Okay, if there are 2 unknowns, you should have 2 equations to be solved. If you have 4 unknown, you will have with 3 equations only, right? If there are 4 unknown, then it automatically falls into indeterminate beams. These things you will analyze in later, like year 4, year 3 or year 4. Now we have only determinate beam. All will follow or comply with these 3 equations of equilibrium. Meaning we are analyzing the beam at equilibrium condition. The good old one is simply supported. It has a hinge here, a small hinge, just a hinge, and then here is a pin, just a pin. It is as though a member is kept onto the points there. Simply supported or hinged or pinned. We can call this as simply supported, hinged or pinned. The notation will be like this. Just at one point it is pinned only, not all together, and the whole cross section is not clamped. Only at one point, say for example, if the depth is 20 centimeter, it may be about 20 centimeter means about 5 centimeter or less than that it will be having a screw here or a pin here. And here also it's just kept on it, right? Just kept on it. It's a point or just a bolt or a nut, just kept on it. And then this is called simply supported. Okay, it may be both at a hinge or both end pinned or one end. The good old example is the one if you go to park garden, you can see the benches there, right? The benches are very good example for simply supported. They just kept on it. People can sit and then they just kept on it. Anytime it can break. I mean, if it exceeds the load, right? And then here is the overhanging beam. Some portion is overhanging on one side, right? One end is pinned like this at this point. The other end is pinned not at the end. If it is at the end, then it is termed as simply supported. Now it is pinned some distance inward, right? Some portion is hanging, overhanging, then the reactions and moments will be different. You need to analyze properly for this case. It is not similar to this case. So some portion is overhanging here, then it is called overhanging beam. No support, no support. It's like a overhanging. Any time it may deflect, right? And this is cantilever beam. Cantilever beam is one is completely fixed, maybe driven into the wall or welded, right? Riveted with the brackets and so on, firmly into the wall, into the structure, into the frame. Restrained, it is totally restrained. Moment is totally arrested for this member. Then and the other end is free. Then it is called cantilever. This cannot be called as cantilever because this end is just pinned only, right? You may think, oh, here also we have free and why not be cantilever? No, cannot. It's overhanging because of pin. If it is fixed here, then it can be treated as a cantilever. I repeat, one end is fixed, other end is free means cantilever. When you see the restrained one, it's just a kind of a roller. You can call this as a roller or just a pin. Meaning what? Okay, I go to the next slide, then it is very clear. I will come back again for this slide after showing the next one. Members with support loadings applied perpendicular to their longitudinal axis or core beams. So always it is loaded perpendicular to the longitudinal axis. If this is a longitudinal axis, loading is on top. If this is a longitudinal axis, loading is on top. Always perpendicular to the longitudinal axis. Then it is called beam. Now, this is an important slide for you to understand the reactions. Take one by one. Example, I go for this condition. Roller support. When you see this condition, right? When you see, don't worry about the inclination. It can be on a plane surface or an inclined surface. Doesn't matter. Let's see one by one. roller on this plane, right? It is acting like this. When it is all about whether the moment is restrained or not, okay? Depending on that, you will have corresponding reactions on the moments. Read here, as a general rule, if a support prevents translation of a body in a given direction, right? When the moment or the translation is prevented in any one direction, then a force is developed onto the body in the opposite direction, equal and opposite to balance out. The member will try to provide equal and opposite force to the restrainment, to the force acting on it. Similarly, if rotation is prevented, a coupled moment is exerted on the body. So in both ways, it may be a force or a moment. In both cases, member will respond in the same direction, opposite and equal quantity, equal magnitude. So if following this, if you see here roller can move like this, right? But moment about this direction is prevented. Moment about this direction is prevented. Hence the member is showing a equal and opposite reactive force for a roller support. Moment is not restrained, it can move because it's roller. Maybe a trolley, crane, trolley, a train, all are good examples. It can move only in this direction. Moment about this direction is prevented if you take in a plane. So the member will show a reactive force or develop a force in an opposite direction, right? In opposite direction where the translation is prevented. There is no translation in this direction, so it will provide an opposite reactive force in this direction to support the member. And then when you come here, in this cable, imagine this cable is pinned at this point. Okay, again, don't worry about the inclination because it follows the direction of force. Later, when you want to go for actual analysis, you have to resolve into respective directions to solve. For now, see this diagram, cable, a pin at this point, right? A pin at this point. Similarly, it can move in this direction, right? It can move in this direction, but not in this direction, right? If you consider to be a plane, it can move like this because of the pin. It can move in this direction, to and fro, but cannot move in this direction. That's why it is applying a reactive force in this direction, equal and opposite, which is F. When you come here also, whether it's upward or downward, it depends on the magnitude and the support. Okay, don't worry about the value, the sign, but it will exert in the direction where it is restrained. So this type of moment is restrained, that's why it's reacting in this direction. And then when you come to fixed support, completely arrested. Completely, you cannot move this way, you cannot move this way. Cannot move this way, cannot move this way. If it is inclined also, cannot move this way, cannot move this way. So it is completely arrested. Movement or translation of the member, right? The reactive force is very effective because it is restrained in this direction as well as in this direction. Because the moment in this direction is restrained, it will provide a reactive force in this direction. And then because the moment in this direction is prevented, right, to and fro prevented, it will react in such a way that by providing a reactive force developed in y direction. Both, here are both. In addition to that, and moment, I already told you for any loading, any restrainment, any type of reactions will be shown by member in two ways. All the vertical forces in terms of shear force, all the horizontal forces in terms of, if there is any stresses developed inside, it is converted into moment. By means of moment or bending, it will show the response. If there is a proper reinforcement, this will not occur because it's inclined, right, at an angle. So I take this one. So the pin, you can move like this. You can move like this, right? Above the pin, you can move like this, but cannot move like this. That's why it is restrained, right? I can even put the arrow here, It is because the moment is restrained in moving in this direction, it will develop a force in this direction And then it is in two components, because it's inclined, the member is inclined, you will have two components, which is X and Y. If it is a horizontal member pin, you will have only one, either Y or X, like the usual questions and answer you're doing for calculation of shear force and bending moment. I repeat, because it's pinned here, there is a restrainment in moving in this direction. The member will impart a reactive force in this direction. And this is not a one, it is in two form due to inclination at an angle, right? The member is not horizontal or member is not vertical. It is fixed at an angle. Hence, the response will have two components, namely vertical and horizontal, like this. And the resultant is shown here. Oh God. Shear force, we are talking about the shear force. When you convert this moment into shear force, right? There is some value here, reaction due to this moment, and there is some reaction here. That's why you have the values like this. And then when you come to loading like this type, there is a load, right? And there is a reaction. When 20 is acting, there will be a 20 opposite direction, then only it is balanced. Altogether, you will have a positive value like this. And then this one, constant UDL, right? Constant UDL. I already told you shear force in a point, if it is a point load, it's a horizontal straight lines. You have to remember this point. If shear force UDL, it will be an inclined line. Meaning the distribution is, start from here, there is, because it's a UDL, it will have a reaction at this point. You have some value here. And then gradually increasing, right? Gradually increasing. It should be cantilever. Oh yeah, fix here, see, fix here. Cannot be like this. It's a fixed end, but UDL acting. Cantilever, UDL acting on it. Because it's fixed, there is a reaction. That's why you're plotting some value here. And then moving on, that is a loading, right? There is a loading and response. Why it is tending to incline in decreasing? Because there is no other support or reaction here. So naturally, it will gradually reduce to zero at this point at free end, because it's free end. In these cases, you have some loading. In this case, you have some reaction. In this case, it's free. That's why it is going on reducing. There is some UDL here, some UDL, go to zero, no UDL at all. That's why it is reducing to zero. You have an inclined line. Moment, coming to moment, because of this reaction, when you go here, this load into distance, there is some load, right? So from here, zero. Starting is zero always, right? Because force into distance is zero here. So start from zero, gradually increasing because there is a moment acting. Load times distance, there is some moment. Moment is a conversion of, combination of force and distance. Because of this moment, slowly increasing to the maximum at this point because there is a moment, right? And also a reaction. No, first is a reaction. From here to here is a response of the reaction. From here until left side of this point is a reaction due to reaction. Reaction into distance. Reaction into distance until left side of this point. When it comes here, there is another moment added, which is this moment. That's why the value goes down. The moment added. And then further, it's all due to the reaction and the distance, right? Goes down to zero here. At this point, there is no moment or distance available, so it turns to zero. This is how moment distribution diagram for a condition of this support, hinge support says hinge or roller support at the ends with a couple acting or moment force acting at the middle. You see here the maximum, okay, better I show with other diagram. This one constant. Coming to constant point load, start here, moment, there is a reaction, right? There is a reaction. There is a reaction, and another thing, reaction not causing the moment here, because it's fixed end, note this point, underline this word. Because it's fixed end, there will be a fixed end moment. So there, either you will derive or you have to remember those formula to apply. Whenever there is a fixed end, it will impart a moment, reactive moment. Because it's fixed, free, no moment, zero. It can move freely. Because it's fixed, no moment, moment is arrested. The member will react to this arrestment. for any loading. Okay. When you come here, because of the fixed end moment, you have some value here. But after this is no loading, but there is a loading and gradually increasing. When the moment after this is, it's all due to gradual decrease, right? It is slowly away from the support, right? It is slowly away from the support. So the value of the moment is reducing until reaching zero at the end. There is no distance or force acting on it, load acting, but there is no distance, so zero. That's how the moment distribution diagram for a cantilever with a point load will be. And then UDL, start from here. Again, because fixed end, you will have fixed end moment, the reaction, not reaction, the resistive moment will be there. Thus, you have some value which is sagging, hogging type. Both the cantilever is hogging type. That's why it's negative at the bottom. Hogging, start from here. You can follow anyone positive or negative. It depends on your convention. So start from here, some value, maximum value, and then it is slowly reducing, right? Because it's a little bit away, right? It will be a little bit away, but there is some loading, right? There is some loading. You see the curve, this is a straight line, but this is a parabolic. Always moment distribution diagram is parabolic for a UDL. Okay, it's not an inclined line, parabolic, because the distribution, the response is slowly, gradually reducing. It is straight reducing at some rate, constant rate, but it is gradually, right, exponential or we don't know what is a parabola it is, exponential or logarithmic or what type of parabola it is. So it will be, in the profile it is gradually decreasing in this way, in this shape, reaching zero at this end. And then coming to this diagram, load, point load. This is all about loading and moments. Again, point load at this point, same similar explanation. When it is acting at this point, there is a reaction. No moments at the end for this type of simply supported, but there will be, because it is not restrained, right? There is nothing to react for the member. It can freely move. That's why moments are zero at the ends. Due to this loading, there will be a reaction only to balance this load. That's why you have some load reaction going to top positive, keep on increasing. At this point, there is another load added, so it will reach here. Maintain the same until it reaches this one, because there is another reactive force. It cannot stop here. There is another reactive force at this end, so it will drop down to zero. Corresponding moment will be, start from here, moment is zero here because simply supported can move freely. Zero moment, no resistive moment offered by the material. Keep on increasing because as you go inside, the distance is increasing and the load is also there. So there will be because of this loading, there will be a gradual increase in moment due to distance, and then reaching a maximum at the middle, then going down, gradually decreasing to zero at the end, because totally away from the, there is no distance at this point. There is some distance, some distance, some distance. That's why you have moments here. At this point, no distance, zero. And then here, constant UDL. I already told you, similar to this one, we can have the explanation for shear force and bending moment. Repeat, there is a reaction. Due to reaction, you have some value. And then loading, right? Loading is a gradual. It is not a point load. It is a gradual loading. Because UDL, you must have an inclined line. It is a reaction is more marked here, some reaction value. And then slowly decreasing because it is away from the support. It is slowly decreasing, right? And this is also UDL, right? I'm sorry, distributed load. Every meter only it is increasing, the load is increasing. It cannot have a constant value like this. It is a varying one, distributed one, right? Distributed one. So it will be slowly decreasing. The force is slowly decreasing because it's balanced out. This reaction is balanced by this load. Okay, there is some load here, some load here, some load here. That's why it started decreasing. Okay, started decreasing. Here, there is nothing to balance out for this reaction. There is nothing. But here, this load, this reaction is balanced by this downward. The balancing is slowly decreasing because it's totally away. Balance is totally decreasing to 0, and then it is increasing in this direction because it's towards another support. So slowly increasing because it's reaching a reaction. Upward and downward is nearing. And then when it reaches here, there is another reaction, big reaction provided by the member. Then it drops to here, this value. That's how the shear force diagram is drawn. Coming to bending moment, I repeat, UDL is parabolic, right? Not an inclined line like point load, parabolic shape. Start from here, free and 0, no distance, free and 0, and then slowly increasing because of the loading to distance is there, very high distance, big one, and then on the other direction it's slowly reducing to 0 at the other end, okay, because the moment is 0 at this point. So it's a parabolic, maximum occurs at the middle, okay, maximum occurs at the middle. You see here, exactly, the maximum bending moment occurs where the shear force is 0, right? The maximum bending moment occurs where the shear force is 0. No loading, so it can free to move. And then parabolic, for this video, this linear type, no need, I don't address too much on this, emphasize too much on this. Triangle load, I'm not giving you in this session. Let's understand these two types well versed. And this is similar to this one, only thing you have to go by the area, easy, or integrate from one end to another end. Easy way is integration or by following the triangular formula for triangular. Or okay, you answer me like this type, right? It may be a pin and hinge with the load F will be WL by FL by 4 or WL by 4 if it is WL by 4. And like this is sagging, point load, that's why it's straight line. The shape of the bending moment diagram will be like this. Just remember, you cannot, for everything you cannot be solving, you cannot be using computer or calculator. Something you have to remember, which is very common for you and familiarized to you, right? Sagging and hogging movements we are seeing here. And this time UDO, parabolic, the distribution is very gradual, not a straight line or a constant rate, like this, parabolic and sagging as well, positive. When it comes to this fixed end, some hogging and some sagging because it's a hinge. There's a hinge. It's not a cantilever. It's a hinge. Because hinge, you have sagging at the end, and then both end fixed. There is a fixed end moment, right? Fixed end moment. That's why you have something hogging, change to sagging, and then hogging. This part you will worry about in your higher classes. When you come here, this is important. Fully hogging, fixed, cantilever, one end fixed, one end free, cantilever, fully hogging, like this box, right? Like this box, bending moment. Couple, it's a couple is acting. There is a couple produced. There is a couple produced. So counteracted, it will act in this. Again, you will study in your higher classes. You will be provided with this table. But if the fixed end moments for this certain type of loading, like point load, UDL, they will give. The rest you have to derive. Okay. Just for your information, no need to remember this thing for now. Right. Summary. At last, the summary, before we go for calculation, the summary is like this. Slope of bending moment always determined by the shape of the shear force lines. Okay. Slope of bending moment always determined by the shape of the shear force lines. The slope of the bending moment always determined by the slope of the bending moment. Here, slope of the bending moment diagram always determined by the shape of the shear force diagram. We'll see. I'll use some more example later. The changes in slope, sagging or hogging also depends on the changes in the shear force values. Okay. There's a correspondence. In other words, shear force is in proportion to bending moment, but it is not always a direct proportion, sometimes indirect proportion. Again, depending on sagging or hogging. When shear force is maximum, bending moment will be minimum, vice versa. That's what I show you already in this diagram. When shear force is maximum, bending moment is 0. When shear force is maximum, when shear force is 0, bending moment is maximum. Shear force is 0, bending moment is maximum. Shear force is 0, bending moment maximum, vice versa. Then coming here, when shear force intersects its axis, there is a maximum moment. Okay, the intersects axis means 0, 1. When shear force is 0, there will be a maximum bending moment. You can follow all these things. When you look, this line gives you the idea of to locate where the maximum bending moment is. You can integrate, differentiate from one end to another end by having an m over x, right? dm over dx from one end to another can find out where the distance is or what is the location of the maximum bending moment. We'll do one calculation like that so that you understand how to calculate maximum bending moment for a given loading and support condition. Shear force and bending moment always start and end with 0 values unless at the point where there is a moment or couple applied. Okay, let's see. Always, most commonly they are end with 0. Most commonly, because there is a loading, there is one. Because there is a reaction, this. Mostly they are ending with 0. Mostly they are ending with 0. End with 0. End with 0. Because it should balance. That's the main criteria. Why they are end with 0? Have to balance. When moment and couple acting, you can take like this: clockwise, positive, anti-clockwise, negative. It depends on about what axis you are going to determine. Keep the clock there. That is a very good idea, clue for you to find out clockwise or anti-clockwise. Keep the clock in front of you or at the axis where you want to find out about which you want to find out. Then it is convenient for you to know which is clockwise and which is anti-clockwise. Continuous beam for your building, and the very beginning I'll show the building. For any building, if you take the continuous beam like first room, second room, third room, fourth room, or it may be a building, house number 1, 2, 3, 4, it is made up of a continuous beam. Their shear force diagram will be like this, like this. I don't want to explain too much on this, I've done already, repeating only. Shear force diagram will vary like this. The corresponding bending moment will also vary like this. You can see in proportion only, right? In proportion, like 0 maximum. There is a load happening at this point, meaning what? There may be a column here, right? Or there may be a wall, partition wall. This part is explaining you the simple calculations for shear force and bending moment. Later we go for more than one member. Let's start with one number first. Or there may be a man standing here. There may be object or any loading crane is kept here, something like that, equivalent to 100 newtons. Okay, 100 newtons. Let's follow the rule. The strategy is important. Strategy will give you what are the types, what are the rules you're going to follow, thumb rules you're going to follow, formula you're going to follow, principles you're going to follow, right? The rule, keep it like this. If I'm changing, please tell me. If it is different from what we are doing, please correct me. But this is what we are following. Rule for shear force, in this case, we are going to draw a bending moment diagram and shear force diagram. Shear force diagram for this case. So in doing shear force, the rules followed are downward force. Downward force, we take it as positive. And then upward force, we are taking as negative. Okay? Upward force is negative. In the bending moment case, bending moment you already know hogging and sagging, right? Sagging is like this, a cup shape, a deep pool like hogging, your beam is loaded with this bending. When you leave like this, it will have a kind of nothing, right? It is stable. When a load is applied in this direction, it will tend to move in this way, right? It will tend to bend like this. I create a sagging type. So create a sagging type. Sagging type. Sagging. Then it is called positive. Same bending, same cantilever beam. Same cantilever. With the example, it's interesting to know. Same cantilever beam. When it is loaded from top, this may be a wall which is supporting this beam at the bottom, which is imparting some load to this, or there may be a wall on top which is imparting this load at this point on the beam. In that case, This is hogging type, which is like this, right? Like this. Hogging is taken as negative. Please remember these points when we are going to do this analysis, which is very important for you. Okay, let's go back to the question there, which is giving 100 newtons and the span is 3 meter. Given span is 3 meter. We are talking about the shear force, right? We are calculating the shear force. First one is shear force. Let's find out the shear force. All of you know what is shear force, right? When a force load is acting vertically, the member is sheared along its cross section, right? The value of shear through this cross section, which is plotted along the longitudinal section, is called shear force bending shear force diagram. We are doing it. We are doing at A. We have done already at A, and then we calculate at B. Okay. What is the value at B? What is the value at B? Moving on from A to A, just keep moving, and then when you go, there is nothing happening after that, so no value changing. Go to B, what will happen? Is there any loading here? If free, it won't do, because it's fixed. It will tend to react to this loading. It will tend to react to this loading. That has to be, because it's restrained here, the member responds due to inertia of the member. It will respond to some amount that should be equal and opposite to the load acting on it, so that the member is kept at equilibrium condition, right? So let that be RB. Okay, when you talk about RB, when this load is coming from here to here, you can use your good old equilibrium conditions, right? The equations of equilibrium, you can use it. Like equation of equilibrium says summation of shear force is equal to 0, summation of moment is equal to 0. And it depends on the direction, whether you're going for X direction, Y direction. Here the loading is acting in one direction, just resolve all of them in Y direction only. Vertical and horizontal loading, then you may have to consider the X and Y separately. For now, just keep it like this. So when you can use this equilibrium equation to solve this, or by common sense, right? By common sense or by arithmetic summation and subtraction, you can do it by observing the diagram, by going through the diagram. Diagram here separately. At this point, this is B, right? When it reaches here, until this point is still 100, right? 100 positive. Only when it's coming here, it is changing to negative 100. Am I right? So until this is 100, we write that point, right? I just put right hand side, left hand side, easy for you. Just right hand side of B, at right hand side of B, just 1 centimeter or 1 mm right hand side to B will be 100 newtons. 100 units. On the other hand, at left hand side, just crossed, or at B, or when you cross, it is crossing a negative 100, isn't it? Negative 100. So at B, let it be at B, because you need to include. It is a cumulative. It's a integrated response. We cannot leave it. We cannot leave the right hand side. So at B, it will be, you need at left hand side of B will be, left hand side to B, to B will be, to B is equal to 100 minus 100, which is equal to 0. No more, nothing is acting. Rest with 100 only. Accordingly, if you draw the diagram, your bending moment, shear force diagram will be like this. Your load is here. Shear force diagram, when you draw correctly, because of the loading, you will have this much value, right? You will have this value. Your shear force diagram will be, starting from here, 100, right? 100. Keep on going, no change until this point. When it comes here, becomes 0. You cannot proceed further because there is a negative, because it falls to 0. Okay. Any question We'll finish bending moment also. Come on, let's do the bending moment diagram. Bending moment diagram will be from bending moment diagram. Let's take the same example. Same example with 10 kilonewton and then 3 meter. Okay, 3 meter. What's happening? At A, start from A. Again, you work from A, you will have the answers for you. Very simple one. I do it in detail so that you are clear with this concept. So, MA is equal to force into distance, which is equal to, at this point, force into distance. Force there, distance at A is 0, right? 10 into 0 is 0. At A is 0. Clear? 10 into 0 is 0. Just move from A to the left. What will happen? Until B, there is no change, right? There is no change. We don't have to bother about. We don't worry about. Even if you calculate every meter, also it will be same because it is one time, right? 1 meter, 1 meter, 3 meter. It will be 10, 10, 10 only. Remains same. Take for example, C. Moment at this point will be load 10 times 1. It will be 10 again. So no need to bother about this. It is there until reaches the point B because there is some restraint, right? There is a fixed end moment which is causing the value to change. Let's do it at next one. At C, it will be MC will be, for example, if you want, you can introduce here. Otherwise, no need. Just introduce at 1 meter for your understanding. 1 meter. Let this be C. At C again, it will be 110 times 10 Newton meter, right? Kilonewton meter, kilonewton meter. And then at B, go to B or D. You can put like these numbers, any number you can put, you will have the same value. And then if it is at 2 meter, it will be 20 because it's adding, right? It means it's increasing. But I will write and see. At D, for example, D, at D, and D, MD is equal to, for example, although the value is not given, for your understanding, we are doing this one graphical way. It will be 20 kilonewton meter. And then moving on, at B, it will be, at B, it will be again F into D is given by 3, right? It's 3, 10 times 3. 10 times 3, it will be 30 kilonewton meter. Correct? So what do? It will bend like this. What is this? Hogging, right? Hogging means negative. Hogging means negative. Negative downward. We plot the negative downward. So it will be just mark 1 by 1, and this is 100, right? And this is 0. At this point is 0, value 0. Then just be increasing to 100, right? Somewhere at C is 100. At C is 100. C is 100. D is 200. B is 300. Join all these points. It's a bending moment hogging, right? Bending moment. And then it is a point load. So point load, you can put it as a straight line. Point load, you can put it as a straight line. Negative, because it's sagging, no, hogging moment. It's a type of a hogging moment. I stop here. Hogging, type of moment is hogging. Hogging moment, which is negative. Okay, this is how you can do for. Guys, any questions so far? The simple beams that we saw for point load at the end. Okay, let's continue. If no question, so I stop here. Any question you can ask me. Solution start with drawing given data or drawing the free body diagram. Okay, free body diagram. When you draw the free body diagram based on the theory, I assume that you are thorough of the theory. Just now we discussed in the class about the basis and the background of different types of supports, different types of loading, and the responses, the member due to its member property, right? Apply all this knowledge to solve this problem. Okay, when for this type of hinge support at both ends, right, we can have conditions like this. Free body diagram will be like this. It will have, due to hinge support, it is free, it is restrained from these two. That's why there will be a reaction due to horizontal and vertical, right? But this is only vertical loading, so you don't need to bother about horizontal right now. Just leave it like that. Because of the vertical downward load, I will have the reaction. If I take this as A, this as B, I will have reaction at this point, which is AY. At support A, direction of Y. And then also here, because it's again a hinge support, I will have a reaction at support B, the direction of Y. And then distances are L by 2, remain same. Just mark here for our free body diagram. The load is, free body diagram is the diagram with the load, reactions and the distances, right? All the given information. P kilonewton, right? The moment doesn't stand alone, it needs a lever on. About a section or a point, you have to take it. Then moving on, we apply X direction should be 0 because there is no horizontal force acting on the member. Naturally, there won't be any horizontal reaction provided by the member. So let's go to the sigma Fy. Take this one, sigma Fy is equal to 0. Summation of sigma Fy is 0. Account for all the forces in Y direction. Sum all the forces in Y direction on this member should be equal to 0. You can start from left to right or right to left. Meaning A to B or B to A. You can go from here to here or you can go from here to here. Have any one direction and then start solving. Let's take from here to here. Let's take from here to here. In this case, all the loading, but I don't put the direction, otherwise confused. It's in the Y direction. We are solving for all Y direction. Take all Y direction forces from A to B. I write down from A to B. Better you write down. Otherwise, you will not know where I'm going. So sigma Fy from A to B. If you solve, start from A is Ray, and then follow the sign convention, which is positive, upward, and then downward is negative for shear force. Accordingly, I will have this one. Ray is positive, and then downward is negative, and then followed by, you have anything else? Yes, you have at the last is RBY, which is upward, again positive. RBY should be equal to 0. From here, I can find RAY. My RAY is equal to P minus RAY2, right? So P minus P, I bring the P this side, and then my RAY, okay? RAY. RBY, right? RBY. Okay. Minus, plus or minus, this is minus, it's going to be RBY, right? RBY. And then same, if you solve from here also, you will get the same equation, but in terms of BY. If you want to know AY, you have to know any one, otherwise you cannot solve for the other. Let's find out what is the value of RBY. How much is RBY? To find out RBY, better we must go for another equation, because two unknowns, must have two equations. This one is also unknown, this one is also unknown. So we need one more equation to solve. Okay, we need two equations to solve two unknowns. So we move on to apply. There is third equilibrium equation. Take moment about A and equate to 0. Let's take the third equilibrium equation so that we can get the unknown. Keep it like this equation 1. And then you solve here, taking moment about. My handwriting is clear. Anywhere not clear, please tell me. Taking moment about. I don't have the version in between. I need the thickness in between. Only the thick and thick, the thicker and thick. Let me try this one. Moment about A. Okay, Moment about A or at A. Moment about A. I will have the answers like this. You start from here. You start from A. You have. Please look into the diagram there. Let me use smaller than I bigger the size. Taking moment about A. From A is or A times moment is force into distance, right? So follow the value from A to B. You're taking from A. About A, right? You're taking about A. So you come from right to left. Okay. Come from right to left. From here to here, A, B to A, because you are solving for A. I just draw the diagram like this. Please remember other things. Always remember the things that we discussed before. If you want to take from A to B, A, imagine the clock is here, the 12, 3, 6, 9. Okay, clockwise anti-clockwise, because moment, right? Better follow clockwise anti-clockwise direction. It is like this, RAB, RBY times the distance will be positive or negative into L. That whole distance is L, right? Whole distance is L. So I will have L, and then this is positive, a negative, right? About here we are taking, it is rotating this direction negative. And then what about the next one? Next loading is this point, right? This P. P is positive or negative? Positive. P into distance is the L by 2, at L by 2, L by 2. Then anything else acting? After this is nothing. At A you cannot account because at A the distance is 0. So you may not have at A values. We have to account for this only. It's not moving. Okay. Come on. Have you done all the loading and the distance? Yes, done. Equated to 0. That's all the forces and moments. Now we can find the unknown RBY. Take RBY this side, then you end up left with PL by 2. PL by 2. So I got my answer. The unknown is ready. Let's substitute in 1. Substitute in 1. You will have equation 1. Substitute in equation 1. Yeah, by 2. This L will go down. End up with P by 2. This is your answer. So you have RBY is equal to P by 2. That's your answer. Right? Let's substitute in this equation, which is P by 2. End up with positive P by 2. So your RAY is equal to P by 2. Very simple. We found out already. Both reactions found out already. We can plot it. Alright, we got the reactions. We can find the maximum bending moment also. To find the maximum bending moment, we have to go through another type of solution, getting the solution. Right. I do part by part so that it is clear to you. Right. Start from. We got the reactions already. We can mark conveniently here. Can we rewrite the drawing, free body diagram to find the moment? The second step is to, the first one we found the shear force reactions. We need to be applying equilibrium forces. You can form the first type of solution is for getting shear force, okay? Or getting shear force or 0 L by 2 to greater than L. That is also possible. If you want to make it very generic one, let me solve by this way. And we already got the reactions. We have to find the moments only. Let me draw the diagram again. You have the reactions already. P by 2 at A, and then P by 2 at B, P by 2 at B, and you have the load P, and these distances are L by 2 already given to you. Now let's find moment. We have to find the moment diagram. So start from this side. We can solve for the bending moment diagram. We have to go from here. At A, you have the bending moment started from A. We have P by 2. moment about A, about A, and about A. Take moment about A, and you have to resolve one by one. As usual, keep the clock at A and do one by one to solve for moment at A. Sigma m, sigma moment at A. Sigma moment at A is equal to 0. I have the answers already. Start from B to A. From B, it is the anticlockwise rotation. So P by 2 into L minus P into, this is clockwise direction. When you keep the clock here, you keep the clock here, if you want, I can put the root. You will have a, what is the number? Where I left. Oh, you need to add another. You know the distance, right? For now, it's simply supported. You know always it is at the middle. With a single load, you can quickly find out that it is a maximum force at the middle. So substitute. Better you find at the middle. For now, I just put it as middle. Later, you will find the distance with another exercise. Similar procedure. Maximum bending moment occurs at the middle, so that is at x equal to, let's find, it's not moment about A. For finding the maximum bending moment, our target is to find the bending moment and shear force, right? To find the maximum bending moment at x equal to L by 2, let's find. Okay, means what? At P. So maximum bending moment, our max is equal to, at this point, either you can keep the clock here and go from A to B, or B to A. Anywhere is possible. Both our goals should be same because it's equidistant, right? Maximum bending moment will be, when you keep the clock here, if you do from A, it will be L by 2 times, right? Reaction, P by 2. P by 2 times, the distance is L by 2, right? End up with PL by 4. This answer, maximum bending moment. To find the distance at which where it is having the maximum, we'll do it. By proper differentiation, you can find the number. For now, just keep it like this, because it's not most important in our case. And then maximum bending moment is found. What else you need to know? Next case, right? Let's go for the next case. Example 5. Oh no, we need to draw the diagram, isn't it? Let's draw the diagram. Draw the diagram. Go ahead. Because you have done. Not selecting. You have the reaction. You have the reaction, right? Reaction and the load. And this is your L by 2 A. This is B. How much is the value here? Let's do one by one. Number 1 is the shear force diagram. Shear force diagram at A. Start from A. How much is RAY? P by 2 then. P by 2. Positive or negative? Upward is positive. So draw it on the top, which is positive. Go ahead. Because in shear force, it's a horizontal lines, right? Point load, it's a horizontal straight lines. There is no other load occurring between A and the middle point. But there is a change at the middle point, right? There is a change at the middle point. It is increasing, the value is increasing. When this is maintaining P by 2 here, there is a download, another download, P by 2 is added. So reach, add another P by 2 here. So the line will go here, right? And then it maintains until this point, the same value. But when it comes here, there is another, until this is P by 2, and there is another P by 2 at this point. So it will get close here at B. So this is how we draw the diagram for shear force. This is positive, this is negative. Okay, negative. Whatever. So positive we put downward. You can use the upward or downward lever to make it different between shear force and bending moment. This is SFD. This is SFD. This is SFD diagram. This is bending moment diagram. To make it different, I put the positive bending moment at the bottom. The maximum value is PL by 2 here, PL by 2, 4, PL by 4 here. And then this is point load, so it will be a straight line. It will be a straight line. Straight inclined line. Bending moment, that's why it is an inclined line. And straight line because it is a point load. It means the distribution is like this. The distribution is gradual and then reaching a peak value, again descending to 0 gradually. So this is called the bending moment diagram, which is positive. Clear? So this one example is solved for simply supported. Similarly, if any calculation, any values are given also, you can solve. Let's say, take this example 5. Example 5 with some value of loading in between, right? Replace the P with 20 kilonewton and then hinge support and then another hinge or pin here, okay? There's a pin here. Take this as A and this as B. Distance as 3 and 3. We can quickly solve this, and because we have ready-made equations with us, equations you know already. RA will be, I don't do too much on this because very simple question. You follow the free body diagram, right? Free body diagram, do the free body diagram, and then I just mark here free body diagram RAY, and then RBY, and then moments. Done, reactions. This is a free body diagram. And your answers for RAY will be, RAY is T by 2, right? T by 2. T by 2. T by 2. Shift T by 2. And maximum bending will be PL by, because we have the equation, ready-made equations, we can substitute. 20 times L is 6 divided by 4, it will be, the answer will be 30, right? Remember, it's like this with the loading at the middle point. 20. This is positive, this is negative. Tn 20 newtons, kilonewtons. So your shear force diagram will be, this is a reaction at A, reaction at B. Shear force diagram will be positive, right? You got 10 here, proceed with no change until this point, but there is a change, added another 10, so it will go up to this one. Maintains this, again another 10 is added, so reaches here, B. A. This is positive, this is negative. Was this one, axis, maximum occurs at the middle, which is positive, so I put it at the downward direction. You can solve for simply supported point load like this. For UDL, similarly you can solve for different conditions, the different distance, 15 kilonewton acting. Can you do the shear force and bending moment? Do shear force and bending moment. Now go to examples 7 with the UDL, another case of UDL. Examples with the UDL. Until this point, UDL should be like this, not so many lines on top, very wrong. Wait, I draw proper one. And the distance is 3 meters. This is A, B, 5. Right, let's do this one. Find out the shear force and bending moment for this condition. Now the same procedure apply, draw the free body diagram. Okay, the free body diagram will be, I put the A beside A, and this is B. So I will have the reaction. I will have the reaction as in this opposite direction because of this loading. RAY, and this one will be RBY. Let's solve one by one. This is a free body diagram with loading everything. First, we apply the equilibrium equations to solve our unknowns. Sigma Fy, Fx no need because there is no horizontal forces acting. I have to use only, I can use only sigma Fy is equal to 0. Applying free body equilibrium equations, you will have sigma Fy equal to 0, which is summation of all forces in the y direction need to be equal to 0. Start from A to B. A is upward, I take it as positive, RAY. Moving on, you have another load called 5 kilonewton, right? How do you account for this 5 kilonewton? Is per meter is kilonewton, right? Like per meter is given, per meter, right? If you take 1 meter, per meter is 5 kilonewton, but you have 3 meters, so it will be times the loading. You need to calculate what is a positive and negative. Download is negative. 5 is per meter, but what will be for total of 3 meter run? That gives you the load. Any other load until B? No. Then equated to no. Is there any other load? All load you have to account for. This load and this one. RBY. RBY is what? Positive or negative? You are summing all the loads that is occurring on the member should be getting balanced. In doing so, we got RAY, upward, downward loading, and then another reaction at B, which is plus RBY. RBY is equal to 0. Right? With that, I can get the answer for RBY is equal to RA. Again, I have the same problem of 2 unknown, 1 equation, right? Let us keep it like that, then we find out the RBY. Right, RAY is equal to, how much is this? Just take this side, you will end up with 15 positive, and when this comes to this side, it will become like this. Keep this as equation 1. You have one equation, 2 unknowns. Let's move on to use another equilibrium condition to find out the unknown. When you solve the moment about A, right? When you solve the moment about A, summation of all the moments about A, start from A, about A, just keep the clock there, 12, 3, 6, 9. When you come from B, RBY is equal to RBY, which is negative, times L is 3 meter, and then for downward force, the force which is acting here will be 15 newtons, right? 15 newtons, but I read in. You have to change to a point load. The loading AB, I need to change to a point load, which is 5 kilonewton meter. I write again, but don't ask me to write every time. You must pick up kilonewton per meter, isn't it? Times 3 is the load. If I convert into point load, it will be 15. Better I write in detail. So it will be loading is 5 kilonewton per meter times 3 will be my loading, right? Times the distance, because the moment, right? Times the distance will be 1.5. Is there any other load about A? Nothing else. 0. We are solving about A. We are not solving for all. We are just solving about A. In this case, this is the equation governing. With this, I can find the unknown RBY. Bring the RBY this side, then it remains here. You have the answer 7.5. 15 times 1.5. 15 times 1.5 will be. Is it correct? Did I do correctly? 3, 3, 2, correct. Substitute this value in, substitute RBY in equation 1. In, what is it? Equation 1. Equation 1. Right? When you do that, you will have the answer. RAY is equal to 15 minus RBY 7.5, 0.5, right? There, 5 and 7.5. So 15 is equal to 15 downward is equal to 15 upward. With that, the member is balanced. You can also counter check like this your answers. and then moments, similar to this moments. Then by applying moments, if you we know that the maximum bending, because it's a one member, we can find at the middle, right? Let's find at the middle at the moment maximum or bending moment, maximum bending moment, max at. For others, you have to find out the x value where it is occurring. I will teach you how to do that. For now, m max at x equal to distance. If you calculate the x distance from here, x distance in this direction, x in this direction, x equal to, you have to find out some distance, right? Middle, take the middle value, which is 1.5 meter. You have the answers like this. About, we are solving at the middle, right? You can go from right to left or left to right, or you go from support B or go from support A. Let's take support, go from support A, right, for the middle point. From support A, it will be the reaction and the loading between these 2 points, okay? The reaction, it will be RAY, it will be R equal to RAY times 1.5. There is another loading also occurring, right? You have one reaction, RAY only. I have already 7.5, right? 7.5 newtons acting here, and then there is a UDL between A and the middle point, right? At 1.5 distance. So just convert this value only. When you convert it, it will be minus downward. How much is the loading? 5, right? 5 kilonewtons. 5 times distance is 1.5 times 1.5 by 2. Okay, 1.5 by 2. 1.5 by 2. That is answer here. So when you do that, you will have. Wait, I repeat, or I remove this one. Maximum bending moment will be, for this case, it will be 5.625. 5.625. 5.625 kilonewton, right? Kilonewton meter. See the answer. So we got the answer. We can plot it nicely like this diagram. Let's see. I use the same diagram here so that you have all the answers done. Let's use the same diagram here. Shear force, start from here. RAY is positive 7.5, and then it's a UDL, so it should be inclined line. Right, it should be inclined line. It's not a straight, it's no longer a straight line. It should be inclined line. Keep on, the load is there, right? There is a reaction, there is another load counteracting. So it will get reduced, right? Because there is another loading coming in, the value will get reduced. So you go down. At one point it will cross 0, right? At one point it will cross 0, and then from here at B, if you check, there is another positive value, which is 7.5. You need to add another 7.5. With that, it will be going down to this value. Hence, it is closing the loop, remaining positive and negative here. This is the shear force diagram. When you come to bending moment diagram, same goes here. For bending moment for UDL is a parabolic, not a straight line, not a straight inclined line. It's a parabolic. You have to remember this point. And then again, it's a positive downward we mark. The maximum value at this point is 5.625 kilonewton meter. So draw a parabolic, going to reduce at this point. Okay, close here like this. Right. I stop here for the calculations. Maybe I have to do one more with the overhanging. I will do it in the next slide. Thank you.
Any question for today's class? I have
posted for you.
Yeah.
For the calculation of the M max, how you calculate the M max at x equal to 1.5 meter? I don't understand the calculation about the last part. 5
Okay.
times 1.5 times 1.5 divided by 2.
Here, right? No, this part. This part? This part, right?
You are not sharing your screen, miss.
Okay. This part, right?
Yes.
Okay. Force is, the moment is given by force into distance, right? So this is the force, right? This is the force. And then multiply by the distance is, we need the moment at this point, the middle point, not at the end. So the distance lever arm will be 1.5. We have to change to UDL to point load first, right? So that you will have the point load, and then you change to the value of, maybe this is, yeah, 1.5. Wait, I rewrite it and show you. One moment. But the distance is 1.5, right? We need the load up to 1.5 only, right? That's why the UDL is 5. I need to convert the UDL into point load for this distance only. That's why I multiply by 1.5, become a point load already. So this load times the distance will be the moment about this point. Okay? First, one moment, I think the pen.
It's but why need 1.5 divided by 2?
Say again. Sorry.
Why need to divide by 2?
Because it is acting at the middle. So it's like this. I go to the PowerPoint and explain you. Easy for me here. Okay, I share this. Can you see the PowerPoint? Here the load is like this, right? I have the distance of 1.5, right? I need to calculate the moment about this section, and I have the reaction here. The loading is unit value. This is 5 kilonewton per meter, isn't it? So I need to change this into point load first. That's why I'm multiplying by 5 into 1.5. Then my number will be changing like this. I put it parallelly. It will become like this. My load will be 7.5 here, right? When I multiply, it will be 7.5 here. 7.5, 7.5. And this is my axis, right? This is my axis. And the distance is 1.5, right? So this load into distance will be half of 1.5. That is why I multiply this by 1.5 by 2. Is this clear?
Yes, clear already.
Okay. Any other question, please? I stop here for class today. I have posted additional questions in CN. If you want, I can show in CN. Or you open and see. I have put another additionally 7 or 8 questions additionally. Please go through that and then solve all of them. Slides also posted already. We will continue. Okay, I have to say one more important information. Chapter 4, I have one more topic pending, the design. Once you finish all these shear force bending moment calculations, thorough of this, it is easy for me to explain the next step, which is design. Same beam will be taken. You will be analyzing the beam for its moment, or either the I section will be given or you have to calculate. Then we move on to selection of the member. So for this, you need to be thorough of this bending moment shear force diagram. Please work out all the 10 questions I have given in the question bank for chapter 5. Finish it. Next class, I finish the design of beams. With that, the chapter 4 will be over. Okay. Any more question?
If no, you can take leave. Thank you. Bye-bye. See you next class. Thank you so much for the feedback.